Next, we will discuss the new idea that is a convergence of a sequence. And let's recall that we already know that a sequence can be visualized by constructing the following, we can call it graph of a sequence. And for example, if we have a sequence defined by this general formula, we can visualize it in the following way. So when n is equal to 1, the term is 1/2. When n equals to 2, the term is 2/3, then 3/4, 4/5, and so on. So at 1 we 1/2. So this is where we label the value. So at A2 we 2/3, 2/3 would be somewhere here. And at 3/4, and it's going to look more like this. At 4 we are at 4/5, and so on. So this is what we know. And what's interesting here is that if we continue plotting, we're going to observe a distinct behavior that previously, when dealing with continuous functions, we would call having a horizontal asymptote. And indeed, if we define a function here using the general formula in the following way, and we graph this function, so this will be a function from R to R, from real numbers to real numbers, this function will have a horizontal asymptote whose equation is y equals 1. And since the sequence resides on this function, the sequence also inherits this type of behavior, and we say that this sequence converges to 1. So we adopt the following notation. We can say that this sequence converges to 1. We can write as n goes to infinity here, or we may omit this because n has to go to infinity. Or alternatively, we can express the same fact like this. We can say the limit of this sequence as n goes to infinity is equal to 1. So let's define what does it mean to have a limit more precisely. So this was just an illustration of that behavior for one sequence, but in general we define, and here I'm going to give a very informal definition. And informal definition of a convergent sequence is the following. A sequence an has a limit that we can call L, or said to converge to L if the graph, again remember this is informal definition, if the graph of ordered pairs n a sub n has a horizontal asymptote-like behavior. So we can say it has a horizontal asymptote, the way we understand it from calculus of continuous functions, as n goes to infinity. So this will be a super informal definition, which is good enough for us in order to understand the concept of convergence. However, there are two other definitions, more formal, less informal. So I'm going to list both of them here, but we're not going to get into details. So let's go with the semi-formal first. We say a sequence has a limit. I guess I should just copy this part instead of just rewriting it. A sequence has a limit L or converges to L if we can make the terms of the sequence as close to L as we like by taking n sufficiently large. So this is less formal definition, which also expresses or describes the same behavior. And finally, we're going to have a super formal definition, I guess. And let me just bring this over. A sequence an has a limit L or converges to L if, again, remember this is very formal, if for every epsilon greater than 0 there is some number n, some natural number n, such that for all other n greater than that value, the following statement is true. So it does repeat the same exact ideas as in the semi-formal definition, except it does it in a more formal way. But again, for the purpose of this class, this definition is good enough. So we say a sequence has a limit if the graph, if it looks like the graph has a horizontal asymptote. Now, we adapt the following vocabulary. We say the limit of a sequence is equals to L as n goes to infinity when we have a picture like this. So we have this horizontal asymptote at L. And your sequence, again, remember, sequence is just the dots. Sequence looks like it approaches to this line. So that's when we say a sequence has a limit L. We can also say that the sequence converges to L. Now, what other types of behaviors are possible there? Well, it is possible that you have the following image. So your sequence may look like this. Just keeps increasing, and in this case, we would say that the limit of a sequence is equal to infinity as n goes to infinity. And then I'm actually not 100% sure on the language here, but we can either say the sequence diverges to infinity, or we can say sequence converges to infinity. But to be safe, we can just say the sequence approaches the infinity and the limit is equal to 0. But again, it's not a converging behavior to converge. If you say to me sequence converges, I would think this type of behavior, but it does make sense if you say sequence converges to infinity. But at the same time, it also makes sense to say the sequence diverges to infinity. Either way. So similarly, but in opposite direction, I guess I shouldn't be drawing dots on the left side of the y-axis. I guess I shouldn't be giving much of the space to the negative side. But if the graph of your sequence looks something like this, then we can say that a sequence, the limit of the sequence is negative infinity, and the sequence diverges to negative infinity or converges to negative infinity. However, it is also possible that you don't get none of this behavior, and you can have a sequence that just goes like this, up and down, like oscillates. It may keep increasing, but if it's none of the three behaviors that we just discussed, then we can say that the limit of this sequence does not exist. Or we can say the sequence diverges. So again, here we can say, let's just use the language diverges to infinity. Here it diverges to negative infinity, and there it just diverges. So the main question that we would like to be able to answer is, given a sequence, does it converge or diverge? So converges or diverges. So for example, we already know that the limit of this sequence is 1, so therefore this sequence converges. Alternatively, we can also graph the following sequence and determine that it diverges to infinity. So the graph of this sequence will look something like this. So at 1 it's 2, at 2 it's 4, and so on. So clearly it diverges to infinity. Now, to help us with this task, we're going to have a theorem, and it doesn't have a name, but we're going to call it a very useful theorem. And this theorem will tell us, it will be sufficient in most cases, but it says this: if you have a function on which your sequence resides, so, or in other words, actually, this says if your sequence is defined by the general term, and that general term can be used to define a function f of x by extending the domain to all real numbers. And if the limit of that function is equal to L, then the limit of the sequence as n goes to infinity is also equals to L. So first of all, notice how it only works one way, right? So if the limit of a sequence exists, it doesn't mean the limit of the function exists. But if the limit of the function does exist, the limit of a sequence exists. And basically what it says is, if your sequence leaves on some function, whatever that function is, but what do we mean by a sequence leaves or resides? Basically, all the points of the sequence belong to the graph of that function. And if your function has a limit, so whether it converges to some value L, or goes to plus infinity, or minus infinity, the terms of the sequence have to follow it, because the sequence literally resides on that function. So if the function converges to some limit, the sequence also has to converge to that limit. So using this theorem, we can only prove the convergence. And let's do an example. Again, let's go back to our good old n over n plus 1. Previously, we have seen the graph of it, so we know the limit is equal to 1, but let's do it the other way. So analytically, we can use the very useful theorem and consider the limit of the following continuous function. Now, what's the advantage of this? It seems like it's just changing n for x, but actually no. We're not just changing n for x. We're bringing all the tools that we have acquired when studying the limits of continuous functions. That is, basically we know the answer. We have, one of the most powerful tools that we have is the L'Hopital's rule. So in this case, we can quickly recognize that we have infinity over infinity. We can apply the L'Hopital's rule, and we take the derivatives, and we conclude that the answer is 1. Now we're gonna be applying the very useful theorem, actually. So the theorem says if that limit exists and equals to something, in our case it is equal to 1, then the limit of the function is also sequence is also equal to that number. So we're gonna go back this way, and we're gonna establish the equality. So the limit of this sequence is equal to 1. Let's try another limit, something more difficult. Let's find the limit of this sequence. Again, we're going to try the very useful theorem. We don't know if it's going to work. It's only going to work if the limit of the function exists. So here we're going to switch n for x. And once again, we're going to recognize this as one of the indeterminate forms. And we're going to apply the L'Hopital's rule. And by the L'Hopital's rule, we have 1 over x over 1 as x goes to infinity. So this limit is equal to 0. So we apply the theorem, and by confirming this, we establish the equality between the two. Now, again, this is example that is not example. So consider the following limit of this sequence. So the sequence will be sine of pi n. And we're going to try to apply the very useful theorem here. And in doing so, we're going to run into the following issue. The limit of sine of pi x actually does not exist. Sine of pi x is just the sinusoid compressed by a factor of pi. So it's just probably looks like this. So at 1 it's going to be 0, so it just crosses the x-axis at every integer. And this function doesn't have a limit, so we cannot establish the inequality because the limit doesn't exist. So does it mean that the limit of this sequence doesn't exist? No, it doesn't mean that. So remember, this theorem only works one way. It only works when the limit of a function exists. So when it doesn't exist, it cannot be applied. So in this case, we're not applying the theorem. However, we can figure out this limit by just being observant and noticing that sine of pi n is always equal to 0 for all values of n. That is, sine of pi is 0, sine of 2 pi is 0, and so on. So this sequence is actually a trivial sequence full of zeros, and it makes sense that it converges to 0. So let's make the following remark. It is possible, so this theorem only goes one way. That means it is possible that the limit of a function doesn't exist, yet the limit of its sequence, which lives on that function, still exists. N is equal to some value L. So we just need to be mindful of this fact when working with this theorem. Now let's consider the following example. This example, we can try to apply the very useful theorem. However, there is a more elegant approach here, and first let's establish the following inequality. The sine of n is always bouncing between -1 and 1, so the following two-sided inequality is true. Now if we divide everything by n squared, the inequality will be the same, will be preserved, because n squared is a positive number. And if we apply the limit to all three sides of this inequality will still be the same, will still hold, because the limit of a smaller function or sequence must be smaller than the limit of a larger sequence or function if both limits do exist. And in this case, both limits do exist. So if this limit was to exist, it will be bounded by 0 on the right and 0 on the left. So the only valid conclusion here is that L, which is the limit of this sequence, is 0. And we call this type of reasoning the squeeze theorem. Let's try to apply the same argument in this example. So here we have the question about this sequence, and the very useful theorem here won't be so useful because -1 to the power of x is not a continuous function. So, however, the squeeze theorem will still work if applicable. So we're going to start by developing the following inequality. So -1 to the power of n is actually bouncing between 1 and -1, and now if we add n to all three sides, nothing is going to change in terms of inequality. And if we divide everything by n, since n is a positive value, inequalities will remain the same way. Now applying the limit to all three sides will give us still the valid inequality. However, we can notice that the sequence on the very right is approaching to 1. The sequence on the very left is also approaching to 1, and therefore the limit of the sequence in the middle, if it exists, will be bounded between -1, sorry, not -1, but 1 and 1, and therefore the only conclusion here is that L is equal to 1. Why? Well, this type of reasoning is called the squeeze theorem, or sometimes it's also called the sandwich theorem, but we found the limit using that theorem. Now, we basically developed a full toolbox for finding the limits for sequences that are defined by the general formula. We can use the squeeze theorem or the very useful theorem, which will lead to possibly L'Hopital's rule, which is pretty straightforward.